Hello everyone. In this set of lectures, we are going to go a little bit deeper into part of the design process. In particular, what we'll do is take up a couple of design examples and try to walk through those and see what are the different ways in which we could go about performing designs. Now, one important thing to understand over here is that these are specific techniques that can be used in order to design digital systems. They are not in that sense fundamental to how digital systems themselves operate or are designed, but it's more a question of how we go about the engineering process. How do we actually go about building large systems? So with that in mind, let's take up a couple of examples. The first thing that I'm going to do is to talk about the notion of hierarchical design. Now, what do we mean by hierarchical design? It's where we start going about designing a system by breaking it down into components. And what we want is to have clear interfaces between these components. So typically, when you talk about something like, let's say, the SoC that powers your cell phone, for example, it's a very complicated system in the sense that it has multiple different parts, and it's more or less impossible at this point for a single person to design the entire chip from scratch, right? So instead, what is done is to basically create this system by integrating a large number of components, and which means that we can basically look at it at different levels of hierarchy. At the top level, we have what we would call an SoC or a system on chip, which of course is not the highest level of hierarchy. The even higher level would be the entire system itself, right? For example, a cell phone would be a part of a design, and one of the design decisions that you would take while building a cell phone would be what kind of chip is going to be the main computing processor that you're going to put inside the chip, inside the phone. Okay, but once we decide on that, inside the chip itself there are a number of other design decisions that we have to make. So the system level in our case would refer to the SoC. Subsystems within that SoC would be, for example, the CPU, the processing unit, memory controller that talks to different kinds of memory and essentially schedules accesses to memory for the CPU. There could be graphics processing units, there could be peripheral communication units, all of which get integrated into a single system on chip. Now, let's say that you want to dig deeper into what goes inside a CPU, then you would start seeing things like, for example, an ALU, an arithmetic and logic unit, cache memory, which is used for temporary storage of data, the register files, which actually perform storage of data for the ALU to operate upon, right, branch predictor units and so on, various other kinds of things. So these would be what we call the module level, because each of these, an ALU or a cache block or a register file, can be thought of as a single module. Typically, it is at this point that it gets close to the point at which individual designers would be working on the system, right? It's essentially impossible for a single person to design an entire SoC. It is very unlikely that a single person would be designing a complete CPU, although it is possible, probably not a very complicated one. On the other hand, an ALU is now getting to the realm of something that you could probably hand over to either a single designer or at least a very small team and tell them, okay, now your goal is to optimize this. But going even further down, you might find that inside the ALU you need to perform addition operations. Inside the register file you need to have optimized registers which have like very fast read response times. The TCQ, the clock to output delay of the register, should be very low, right? Similarly, the setup times and so on should be well optimized. So in those cases, what you would very likely find is that these are now at a small enough level that individual designers could probably be handed over a particular task and told, okay, this is a component that you need to design. The components that you need to design will in turn be used in order to build up modules. Those modules will be used in order to build up subcomponents or subsystems, and the subsystems will finally get integrated together to get you your final system. Okay. So this is essentially what we mean by the layers of hierarchy that we go through while designing a system. Now, of course, this is not unique to electronic systems or electronic design. It applies in pretty much anything that we can think of as a design process, right? So whether it is engineering, let's say that you are designing a car, you do not just come up with a car magically all by itself, right? You first decide on what kind of engine goes into it, how the chassis should be built, what kind of wheels need to go onto it, what kind of tires need to be used, what kind of the seating arrangements, how are they going to be placed. All of those are different decisions. So those would be sort of the subsystems. The engine, for example, is a subsystem. The music and entertainment would be another subsystem. Internal cabin cooling, air conditioning would be a subsystem, and so on. So pretty much any engineering task can be broken down in this way. So hierarchical design is a sort of a fundamental part of the engineering process. Now, why do we do it? Basically complexity management, right? Designing a complete system all on your own is very hard to keep track of everything that is happening in there. So instead we opt for abstraction and modularity. Essentially, if we are able to break our system into a set of interconnected modules, right, where we can focus just on module interfaces rather than the internal details of how each module works, then it makes it much easier for us to design a system. For example, if we can, for example, say that our CPU is going to have the AXI bus protocol, is going to follow the AXI bus protocol in order to communicate with memory as well as other peripheral devices, that frees up our choices of what kind of devices we can build, and every other device just needs to be built in such a way that it's now compatible with the AXI bus standard, right. So this is meant by a module interface, right. This is what I mean when I talk about a module interface. The interface is this bus interface, which basically tells us that the CPU can talk to any peripheral provided that that peripheral follows this particular bus standard. Now, how exactly do bus standards work and so on is something that we will be looking at in more detail later. But for the time being, you can sort of imagine this as a level of abstraction. We do not need to know how the peripheral or the memory block internally works, provided that I can say that I can give it an address, I can give it some read-write enable signals, I can give it data if I need to write, and whether it's a read or a write operation will get accomplished automatically, right. So as long as I can have that level of abstraction available to me, the person designing the CPU does not need to know how the person designing the, for example, the UART device, right, how that person is going about designing the internals of their system. This also enables reusability of code, right, because we now have abstract interfaces, and let's say that you upgrade your CPU, the rest of your interfaces may remain the same. It enables parallel development for the simple reason that now that we have broken these things down into separate units, it's no longer one person who is the bottleneck. Each individual unit has been specified at a sufficient level of detail that different people can work on the parts and integrate them finally. It also actually helps with verification. Verification basically being how do we verify or test that a particular design is working correctly, right. So the whole notion of test benches, right, revolves around this idea of verification. We want to verify that the design that we have got works the way that we would like it to. Ultimately, it also means easier maintenance, right. And as you might imagine, this basically should make it clear that this is not necessarily a set of purely technical decisions that we are taking over here, right. There are of course certain technical aspects in terms of how we design interfaces, how much expressive power is available in each interface, how well defined is an interface, how testable is an interface, and so on. Those are things that you can actually quantify in scientific terms. But at the end of the day, how easy is it to maintain is not really a scientific quantity, right. It is something which comes about more from the fact that there are people working on it, and how it's based more on sort of the experience that people have developed over time of working with such systems. So there are a few general principles that apply when we are trying to perform top-down design, the whole idea of hierarchical design. The two most common approaches are what's called top-down design, where what we do is we start out with a system level specification and then we decompose it into smaller blocks. The design that I talked about earlier, right, for the CPU over here essentially started out with a system level specification and then said, okay, I need these subsystems in order to build that system. In order to build the CPU subsystem, I need these modules. In order to build the ALU module, I need some components such as adders and so on. So this is a top-down description, right. Now equally well, we could also have thought of it as bottom-up. Maybe the way to think about it would be, there are people, maybe they are beginning just learning how to do digital design. Okay, we know how to build adders. Now that we know how to build adders, we are no longer satisfied, right? We don't just want to add numbers together. We would like to say, okay, how do I build one module that can do either addition or multiplication or shifting, maybe based on some kind of selection operation that I provide to it. And that basically leads me to the idea of an ALU. And I can create an ALU where it can perform multiple different arithmetic or logic operations depending on some kind of selection unit. Now once I have an ALU and I also maybe decide that I am able to build up some kind of a register file, and I have a couple of other things that I put together, I suddenly find that the basic idea of a CPU now comes into play, right? I can build up a CPU out of this. And once I have a CPU and I have the notion of memory and I have the notion of certain peripherals that I can attach to it, I can actually start thinking of a system on chip. That would be going in the opposite direction. It's called the bottom up flow, right? So in the bottom up design flow, we first design the basic building blocks, we combine them to create larger modules, and in particular, one thing that we will find over here is that we tend to make a lot of use of reusable IP blocks. So we actually look for, okay, are there blocks that are already available and can I use them as part of my design? Can I sort of combine them with something else that I already have? Now of course reusable IP, it's not that top down and bottom up are mutually exclusive or that they are different, fundamentally different approaches. And in fact what is usually done is some kind of a meet in the middle approach. And what we mean by that is there would typically be teams of engineers who are working on various kinds of reusable IPs, making better and better adders, making better register files and so on. And at the same time there are the other architects who are working from the top down and saying, okay, this is what we need in terms of having more registers, a larger ALU, a faster addition unit and so on, right? And at some point they both sort of see what each other has got and they can meet in the middle and decide, okay, this could be a good way of building up the overall system that we want. So these are not sort of mutually exclusive or fundamentally different design approaches. It's just the way that you look at the problem. Ultimately your goal is to be able to solve the problem, to build what you need. Now the key part in all of this is what we can call interface definition, right? And what I mean by interface definition is we want to clearly define the inputs, outputs and the functionality of each and every module that's there in the system. So if it's an adder, I need to be able to say, okay, it takes these inputs, maybe two 8-bit inputs, and produces an output which is, let's say, an 8-bit sum output and a 1-bit carry or overflow output, right? So that's a clearly defined interface for an adder. As it stands, it does not need a clock, it does not need a reset signal, but if I change the implementation of my adder, I might find that I actually have registers inside and maybe now I need to also have a clock, I need to have a start signal, I need to have a done signal, a few other interface signals. As long as those interfaces are clearly defined, the actual internal implementation does not matter. So as you can imagine, when we do this, we have multiple different abstraction levels when we are talking about a system, right? We could talk about things at the system level, we could talk about things at the algorithm level. So for example, you might even have different ways of performing multiplication, right? Those are different algorithms that you could choose to implement within your hardware. And then of course we have RTL, the register transfer level, where we have actually broken things down in terms of what data needs to be stored in flip-flops and what computation needs to be performed with that data as a sequence of steps, right? That's going to be the primary focus of course as far as this particular course is concerned, right? And we'll be talking, most of the examples that we take will be at the RTL level. But RTL is not the end of the story. In order to actually implement something as hardware, you need to go down to the gate level. And what we will be doing here is basically taking compilers that are able to take RTL designs and push them down to the gate level.